Okay, welcome back. So today we're going to go through the process of fitting principal components analysis, which is actually pretty easy to do once you understand the code to do it and you have your data formatted in a way to fit the model. And most of the time, some of you already know this, most of your time is spent getting the data properly in order before you fit the model. Fitting the model is usually pretty quick. And then for those that are wanting to plot outputs, that's the other big time sink. You spend a lot of time trying to make a plot that's interpretable. And that's what we're going to spend some time with today. So we're using the packages vegan. This is the community ecology multivariate stats package. We're using the package Ggplot2. This is the grammar of the graphics plotting. We're using biodiversity R. This is another community ecology package, and importantly has a function that allows us to test which of the principal components we want to retain for interpretation. And then we're using the package Ggvegan. So this is the grammar of graphics from Ggplot applied to outputs from the community ecology package vegan, okay? And I have already loaded all of those. And we've spent a lot of time in this class this week and last week getting biodiversity R and Ggvegan loaded. So the take-home messages one more time, just so that it's on the recording, is update all of your packages. Make sure you're using the newest version of R, which at the time of this recording is 4.04 Lost Library Book. Update all of your packages and then do those installs at the beginning and before you have loaded other packages into your workspace, okay? And then Ggvegan is available on GitHub, not on the CRAN, and I just posted a video today to show you how to download Ggvegan, okay? So with those libraries or with those packages called through our library, and I did that, loaded all of those, we're just going to start by fitting this PCA to some data that we've spent time talking about this semester. This data, mpg miles per gallon, that came from the Ggplot2 package. And when you run that data, you should notice that over in your environment, you now have an object called mpg with 234 observations of 11 variables. We're going to just pull out a few of those. We're going to subset the data to grab engine displacement, city fuel economy, CTY, and highway fuel economy. That is the third, the eighth, and the ninth column from this mpg. And so the next little bit of code here is just indexing that. We're creating a new object called mpg_pca, and we're indexing mpg. That's what these square brackets represent. Inside of those square brackets, there's always a comma. Everything before the comma represents rows in the data frame. Everything after the comma represents columns. Then we're using the concatenate function, which means to just go through within parentheses after that and grab, in this case, columns 3, 8, and 9, okay? So we can run that. And we get this mpg_pca. We still have all of our observations. That is, we still have all of the rows, but now we are only retaining 3 variables, okay? And this is a very simple variable reduction or dimensionality reduction procedure. Keep in mind, if you're fitting a PCA to high dimension data, much more than 3, that's where it becomes a very powerful process. And remember, it's sometimes referred to as a heuristic process or an exploratory process. We want to see patterns in the data. We're not necessarily testing a hypothesis. We're not going to have a p-value come out of this. We're just exploring patterns in the data, okay? So to run a PCA, remember when we talked about direct and indirect ordination, there was a direct or constrained ordination called redundancy analysis, RDA, that was based on data that fit a monotonic response. And then and that's 2 matrices, usually in ecology, environmental, and community data. But the unconstrained or indirect counterpart to that is PCA, where you just give it a single matrix, and we think about a monotonic relationship within just a single matrix, okay? So RDA is the function, and that's where just having a little bit of understanding of multivariate stats so that you can plug in that, that function RDA, but understand that it's actually running a PCA because within the function, we're only giving it a single argument, and in this case, that data frame that we just created from those 3 variables, okay? So we're going to run this. And it took just a moment. It ran pretty fast. It created an object in our environment up here called Pca1. We're going to have a look at that. This next line of code, we're just going to run Pca1. It tells us, it reminds us of our equation that we fit, the line of code basically. It tells us the total, what it refers to as inertia or variation or variance in the data. Then it tells us the amount of that is unconstrained. And because we're running unconstrained or indirect ordination, it's all unconstrained. If we had a second matrix in there where we had environmental variables and we were trying to explain variation in community structure using environmental variables, the amount of variation that's explained is the constrained portion, okay? And so when you're looking at direct ordination or constrained ordination, you'll have another column here that shows how much of it was constrained, how much of it was explained, or how much of it was unconstrained, or what was left on the table as unexplained, okay? And then it tells us for each of our principal components, how much of that total inertia was captured by that PC. So 53.56, that's the lion's share of 55.28. So PC1 is the main axis or eigenvector that we might want to interpret, okay? And we can get a little bit more information if we run this summary function with Pca1 inside the parentheses. So we run that. I'm just gonna expand this window. We've got 234 observations. So those observations are referred to as sites. And then we've got the 3 explanatory variables. Those are referred to as species. Okay, so I'll go all the way back to the very top here. Notice this information is pretty much the same thing as what we just saw. It's now calling it eigenvalue instead of constrained inertia, but it's the same principle. It also gives us a little bit more information on the proportion of that. So it's just taking this 53.55 and dividing it by 55.24 to determine that 96% of the variation is explained in PC1. And then PC2, it's about 2%, PC3, it's 1%. Then it gives you the cumulative amount of variation explained by each of those. And that will always reach to 1. And remember, it creates a PC for every variable that's in your original data set. So if we had 30 variables in there, we would have 30 PC axes. Of course, we don't want to think about all 30 of those. Our main interest is what's the minimum number of principal components we can retain to understand the patterns in the data, okay? And so it tells you the scaling that we're using here. And remember, and when we talked about ordination in a couple lectures ago, you can scale the data differently to look at either covariance or correlations in the variables that have been loaded in there. And scaling too is by far what's used most. Okay, most of the time we're thinking about what are the correlations between these original variables and how do those play out across these PCs that we're fitting. Okay, so the default was scaling 2. If you get deep into PCA, you can go in to RDA ? And explore how to change the scaling to 1 if your interest deviates from what we're generally fitting within a PCA. Okay. The species score, so here's our original variables, and these are the coordinates along PC1. That's the loading for displacement. Notice it's positive, so if we lay out that PC axis, this would be, it's always centered on 0, and this would be off to the right. And then notice city fuel economy and highway fuel economy are both negative. If we plot it in 2-dimensional space, and most of the time you'll see 2-dimensional space for PC plots, just even if we're only interpreting 1, it's nice to be able to see the scatter of the data in 2 dimensions, and it gives you the coordinates. So here and here are XY coordinates in a biplot, and that's what we're going to show in a minute is a biplot of these data. And then you can think about within that multivariate space, where do each of the observations fall out, and those are the coordinates of each of those observations. Okay. So then the challenge is, how do we determine which of those PCAs to retain for interpretation? We know that the first one is always going to explain the most variation, and then the next most will be in the second one. But at some point, meaningful patterns in the data transition into statistical noise that we want to essentially ignore. That's the whole purpose of reducing the dimensions of the data. And I shared with you that paper from Jackson in 1993 that was thinking about stopping rules in PCA in this idea of a broken stick model, where if you take all of the variation and you put it into a monotonic reduction of variation, then you can plot each of your observed variation explained by each of the PCAs. And where your observed is greater than the expected under the broken stick model, those are the PCs you want to retain for interpretation. If you don't want to deal with doing that by hand, this is where this biodiversity R package that took so much time to get installed, because there's a huge number of dependency packages on there. But inside that package, there is a function called Pca Significance, capital P, capital C, capital A significance. Then you just give it the model that you created earlier. Okay, so you can run that, and if the package is loaded properly, you get this very nice output where it reminds you of the eigenvalue for each of your PCs. It reminds you this time of percent, so it's taken those proportions and multiplied them by 100 to give percent variance. It gives you the cumulative percent variance. It tells you what the broken stick model shows, and it shows you in terms of percentages and then cumulative. And then this row right here is the one that we're interested in, okay? This percent explained by the observed PCs that are greater than what the broken stick percentage represents. And notice that this has a 1 for PC1, so we would want to retain PC1 for interpretation, but PC2 and PC3 we can essentially ignore from the purposes of this PCA analysis in terms of an interpretation. Most of the patterns in the data for these three variables are captured in the first PC. So we've reduced the dimensions of our data from 3 variables, displacement, highway fuel economy, city fuel economy, down to a single linear combination of those variables called a principal component. And that's what we would retain for analysis, PC1. And as I said earlier, a lot of times you'll see PC1, even if PC2 is not meant to be retained for interpretation, we still might plot it against PC2 and just pay attention to how the data are distributed along the gradient that is represented by PC1, okay? So fitting the model, pretty straightforward. We did that in a single line of code because the data were in order and they were ready to fit. Interpreting the model we could do with the summary function, but much more meaningful information comes from this Pca significance, okay? Then the last part is plotting the data and thinking about what does it mean. And this is the part that can be very frustrating in multivariate statistics. There's a lot of variables. We're trying to show a lot of information in a small number of dimensions. So Autoplot is a function from Vegan that will give you a very basic plot, okay? And I'm going to show you what this plot looks like. So you don't need any sort of package to run this. As long as you have Vegan loaded, you don't need any packages beyond that. You just run this, and notice we now have a plot here. And we can zoom in on this, maybe, yep. So each of these points represents a vehicle in the case of our data, and where they fall within multi-dimensional space along PC1 and PC2. And then each of these crosses, these red plus marks, represent the original variables that we loaded, okay? But notice nothing is labeled. This is just the data cloud and what the unnamed variables, what their loadings are along PC1 and PC2, okay? So perhaps of minimal use from a heuristic approach using this very basic plot. There's a lot of ways that you can improve that. We won't go into too much detail, but you can do something as simple as just changing the type to equals T with quotations around the T, which stands for text. And what that's going to do is replace all of those points with text, which is helpful for thinking about the original variable. So here's city, here's highway, here's displacement. But the cloud of data and the amount of text that's there means that unless you're thinking about an observation that's on the outskirts or on the fringe of the data cloud, you really can't read what's going on in there. And that's pretty typical if you have a large number of observations. So what you typically will see is that these observations are shown as points, and then text is used to show the loadings of the original variables, okay? So better in terms of understanding the nature of the data, because now we can interpret PC1 in vehicles that have positive scores along PC1, have high engine displacement, and low city fuel economy and low highway fuel economy. So these are vehicles with large engines and low fuel economy. And then as we go negative along PC1, we move towards engines or vehicles with smaller engines and higher fuel economy. So this is our first gradient, is a gradient in engine size and fuel economy shown together. And so we've reduced the amount of variation from those three variables to just thinking about this first axis here, okay? And this is one of the criticisms of PCAs actually, is if you're interested in the patterns with the original variables, you can no longer interpret those independent of each other. This PC1 is a linear combination of those, okay? So those variables are linked together. You wouldn't want to interpret PC1 as primarily a gradient in engine displacement because we have also included city and highway in there, okay? And so critics of PCA say, well, you lose any sort of information about your original scale of the data of the variables, which is true. Okay, so that plot's a little bit better, but you probably have never read a peer-reviewed publication that used the basic plots from Vegan because it's just hard to interpret that. And this is where this package Ggvegan comes in, okay? And I've hashed out how to install that. For those that haven't watched the other video, you could just remove these hashtags, but I would recommend installing this in a new session, not midway through like this. But anyway, this was developed by Gavin Simpson. Ggvegan's the name of the package. It's available on GitHub, okay? And I've already loaded the library, so I'm going to skip that. To run an autoplot, so there's a function. It's autoplot .pca, but you can just type in autoplot. And as long as the first object or argument that you give within that function is a PCA, it'll automatically determine the type of plot that it's going to create. Okay, so autoplot PCA, and I've changed the default legend.position to none. So I'm taking the legend out of there, and the legend is just going to tell us that it's either site observations or the loadings of the original variables. Okay, and you can do $autoplot.pca and learn about the defaults, and that's how I learned to do this legend.position equals none. Okay, but then so this is, remember, grammar of the graphics is we usually use the function ggplot, then we tell it the data, then we tell it our mapping or our aesthetics. And it's very similar. This is the same grammar of the graphics. We're doing autoplot, we're telling it the PCA, and in this case, that's all you really need to tell it if you're okay with there being a legend on there. But then you can layer complexity on top of that, just like ggplot. So now notice I've got the plus sign, and we always put the plus sign at the end of the line of code. And then xlab stands for x label. I'm going to change this default PC1 label to PC1, but parenthetically 97%, representing that 97% of the variation in the data is captured by PC1. And notice I just put all of that in quotations. That's whatever's in the quotations is exactly what's going to appear on the x label, x-axis label. Then we do plus, and we do the same thing on the y lab. So here it was 2%. Then I've gone in and added a little bit of extra code here to create these dashed lines that go through the origin. And typically you want to show the origin of the data because it's not always perfectly centered. Notice here, because the high loadings or the large negative loadings of city and highway that were not centered on the origin. So it's always good to show the origin of the data because it's not always in the center of the graph. And so to do that in ggplot, so all of this applies to ggplot or Ggvegan, we just do geom ab line, and so that's for a horizontal line, and then geom v line is for a vertical line. For ab line, we just give it the intercept and the slope, so it's going to go through 0. The slope's going to go through the slope's going to be 0. The line type is dashed, And then the size of the line, you can make it thicker or thinner by changing this size, okay? And then for V-line, here we need to tell it an aesthetics argument where we want it to have an x-intercept of 0. So we want it to go through the x axis at 0 and then go vertical from there. Line type is the same, dash size is the same, okay? And then I've added a theme on here, okay? And so when you first run these Ggplots, as we've already explored a bit, you get this gray background with major and minor grids on it. And the way to remove that is within this theme argument. So theme is like basically the theme of what does the graph look like. And I've just gone in and changed panel.grid.major, which is the major grids that go through the back of the panel. And in Ggplot lingo, you just do element blank, and it's going to take those away. Okay, then I did a comma, and I went to the next line. So all of this is nested. Notice all of this is nested within theme, okay? I just did the comma and went to the next line so that we're not chasing code across the screen. Now I did panel.grid minor and did element blank, same thing. So the minor grid elements that go across there will be gone. And then panel.background will remove the gray. If you do the same element blank, it'll just be a white background. And then axis line, element line underscore line black is just going to create black lines for each of your axes, okay? So some of that is very redundant with Ggplot, and if you've never seen these before, that's all explained in the help for either Autoplot or Ggplot, okay? Because they're both using the same grammar of the graphics, okay? So that obviously a lot more effort went into that than creating here, but let's have a look at what it looks like relative to the basic plot. So now this is much more like what you would expect to see in a publication. So now we have PC1 with the explained % of variation there, and PC2 with the same thing. We've got these dashed lines going through the origin. We've got the scatter of data, but we didn't use text. We just used here the default red dots. And then we have vectors or arrows that start at the origin and go out to the names of the original variables, okay? And then those are labeled with text. This is the minimum basic information you need to interpret a PCA, okay? So Autoplot, that came from ggvegan, which is a little bit of extra on top of it, gives you a very nice publishable plot. If you're at the kind of heuristic phase of exploring the data but not publishing this, this might be all that you really need. But if you are interested in publishing this, you might want to go a bit further and do things like change the color of these points or change the shape of these points. And Autoplot does not, in the ggvegan, does not currently allow you to do that. Okay, so the last little bit of code that we're going to go over is how to grab the output from vegan, fortify it using a function called fortify from ggvegan, and then feed that straight into ggplot, where we have remarkable control over every aspect of the plot, including the color and shape of the points, okay? So this last bit of code here then is how to grab the output. I'm just going to minimize this. Is first how to grab the output using fortify, and then everything else is just detail for how to make that a plot where you're choosing every aspect of what it looks like, okay? And rather than ask you to hack out all of that code on your own, I just did it for you, and you can always just go back in and modify this, okay? So ggplot, this will be a review. We've talked about a lot of this stuff already, but ggplot is so complex. There's always more out there that we haven't talked about. I know one of the complaints about ggplot is there's a pretty steep learning curve there, and I get that. And I've tried to give you some of the basics here so you don't have to start on your own. But let's start with the fortify, okay? So this fortify is a function from ggvegan that allows you to just grab the output from that PCA and store it in a data frame or a tibble that could then be read into Ggplot, okay? So we're just going to create this object called PCA_fort. We're going to use the fortify function. We're going to tell it PCA1, and then we're going to tell it axes 1 and 2. Now remember, we only really want to interpret axis 1, but as you can imagine, if we didn't have PC2 on here, this scatter plot would just be a bunch of points along a single axis. And you could do a histogram maybe, but it's actually really nice to be able to interpret the scatter of the data vertically along this second axis. Okay, so we're going to grab axis 1 and 2. If you have very complex data and you need to retain PCA1, PCA2, and PCA3, this happens sometimes. You could choose to grab axis 1 and 2 and create that plot. And then typically what I see in the ecology literature is a second panel that shows PC1 versus PC3, okay? And we always show PC1 as the X because that's the one that explains the most variation. And then we're just changing the Y-axis to explore those higher dimensions, okay? So for now, we're going to fortify and just grab axes 1 and 2, okay? And then the next bit is just code that is related to the points, the arrows, the text, the vertical and horizontal line, the axes, and then the theme, okay? And I know to new users, this is a lot of information, but you know, the whole point of the grammar of the graphics is we should be able to decompose that into manageable units, okay? So we start with Ggplot, but notice now I'm just giving it Ggplot without an argument of the data and without an indication of the aesthetics that we want to map. And the reason I'm doing that is we're going to change the aesthetics for the points, for the segments, and for the text. And so rather than applying the same aesthetics across each of those, we're going to change it within each of the subsequent geometry arguments, okay? And Natalie, I think this is what we were talking about one day. It's like, why is it that sometimes you see the aesthetics argument here and then sometimes you see it here? And that's because they're creating a very complex plot here where we're going to change a lot of colors, okay? So geom point, we've seen this before. That's what's going to create the scatter plot. We tell it the data. We're going to, in this case, subset it to just the sites. Remember, there's species and then there's sites. The species are the original variables. The sites are all of the observations. And we usually show those observations as just a cloud of points. So for data, we're subsetting or nesting the subset function within geom point, where we're going into PCA fort and we're just grabbing scores, okay? So if I go over here and show you PCA fort, notice there's score is species or sites. And we're just going to start by grabbing the sites, okay? We're going to plot these first. That's what the data subset is doing. It's searching this score column and grabbing, in our case, score is absolutely equal to, so 2 equal signs, and then sites, okay? So we're going to grab those first. Now we're going to tell it AES, and notice this is nested within geom point. So I did mapping equals AES. Most of the time we just type AES. But what we want to show is from this fortify, we have PC1 and we have PC2. So we're going to plot on the x-axis PC1 and on the y-axis PC2. Then there's another comma. And we're going to change the color of those points to black. So here they were red. You can't really easily change that from the Autoplot. But in Ggplot, you can pick any color you want. And there's all sorts of colors that are listed in R. A lot of them are intuitive, but there's a great diversity beyond just those that are named. There's a color coding system, and you can use any of those colors here in Ggplot. Okay, and then there's a comma, and the last little argument here is alpha, and alpha represents transparency. So an alpha of equal to 1, I think, is totally solid, and an alpha equal to 0 is totally transparent. If I'm remembering, I might have those backwards, but 0.5 would be it's half transparent, okay? And the reason for doing that is when you have a cloud of data, like we see over here in this plot, when points are stacked on top of points, if you make those slightly transparent, when points are stacked on points, they'll appear as much darker or a higher density of points than places where there might be just a single point. And so it's a way of showing high density areas of the data cloud by changing this alpha, okay? Everyone okay with me so far? We're just really taking a deep dive into the arguments of geom point. All of this is explained in the help section for Ggplot 2, okay? So then geom segment, that's what we use to create the arrows, okay? So we're gonna create these vectors that go from the origin to the coordinates of our original variable. So here, this should look familiar. Our data is a subset from Pca Fort, this time absolutely equal to species. So we're just gonna grab those three variables. And then we tell it, in this case, our mapping, AES, is the center of the data cloud. So X is equal to 0, Y is equal to 0. It's gonna go to the origin of the data. Then we're gonna tell it the X end and the Y end. And those are the coordinates from PC1 and PC2 for the species, okay? So it starts at the origin and it goes out to the XY coordinates of each of the original variables, okay? That's what X end and Y end represents. Then we can determine something about the arrow. So we want these to be vectors, have arrowheads on them. We can just do arrow equals and then the arrow function. We can tell it something about the length and then the original coordinate system, okay? So this NPC is probably what you will always use when you're plotting the data in the original coordinate system, okay? And then the length, the 0.3, determines we're gonna have arrowheads on the end of that, and you can make those arrowheads long or short by changing that length, okay? And then the type, so in this Autoplot over here on the right, those are opened arrowheads. We're gonna show closed arrowheads, okay? So you have a lot of control over what the arrows look like. And of course, we have control over the color. I just put in dark gray as an example here. And then the thickness of the arrow is the size here. And so we can make them really thin or we can make them really thick, okay? All right, so then we're gonna layer over a little bit more complexity and we're gonna do geom text. We're gonna add text onto this. And the text is gonna be for these species. We wanna put in CTY, highway, and displacement on there. So here, this should be really familiar by now. We're doing the subset Pca Fort. We're grabbing species again. We're mapping the AES. So we're gonna show the label. We're gonna do PC1 coordinates, and then we're gonna multiply it by 1.1, which just pushes it a little bit past the coordinates. And the whole point of doing that, if it was a 1, it'd be right on the coordinates. At 1.1, it's just moving it 10% of the way away from the end of the arrowhead. And the reason we're doing that is so that the text doesn't end up right on top of the arrowhead, okay? So that, and if you wanted it further away, you could do 1.2. It would put it 20% of the way, and so on, okay? And so we're just multiplying the original location on the axis by this 1.1, and we're doing the same thing on the y-axis, okay? So that's how you can add text on top of it. Okay, so and then we're going to layer on top of that these lines as we talked about earlier. So we've got the ab line to do the horizontal line, and the v line to do the vertical line. And those arguments are the exact same. But now notice we have control over the color. We can change that. In this case, I did gray so that they're a little bit lighter than the dark gray for the segments. Okay, X lab and Y lab we've already talked about. And theme we've already talked about, okay? So after much explanation on that, we can run this. And we now have a beautiful looking plot of our PCA that has the data cloud where the data points are slightly transparent. So where it's dark, there's a lot of points stacked in there. That's a heavy density, a lot of observations that are very similar. And then when we move away from that, we can see the density of the data. We have these closed arrowheads that are dark gray that are going out to our original variables. If you wanted to move those over, you could adjust that 1.1. We've got black text, but we could change the color of the text. We've got our PC labels that give the % variation explained. We've got these light gray dashed lines going through the origin. Okay, so in my lab, we would save this as a TIFF or a JPEG or whatever the journal wants, and we have a publication ready plot there that that can be submitted, and we were able to do that in Ggplot. Okay, not without a lot of effort, but now that you have this code, the trick is just kind of understanding where to change points of that so that you too, for those that are interested in making a Pca plot, can do so. Okay, and then the last thing in here then is just a coding challenge. Okay, and the idea here is to not have you go in and rehash all of this, but to just change minor things with a new data set, so that you kind of understand the basics for how to manipulate this code to fit your own interests and own purposes. Okay. We can stop the recording and I can just release everyone on this, but the challenge is to grab a new data set called Iris, create a PCA of the first 4 variables. So there's 5 columns there. The last one is the species. I want you to drop that one. Just plot the first 4 in a PCA. Calculate the broken stick model. That's that single line of code. Pca significance tells you which of the PCs you want to retain. And then the last one is to plot it, but to color the points by the species, which is the 5th variable. Okay. And just as a hint, the way to do that is within geom point. You want to, that's where you're going to insert a color argument that's equal to species. Okay. Any discussion? I know we went through a lot there, but you know, it's all pertinent information, I think, for those that are really going to use a PCA later. Everyone okay?
I had a question about interpreting the graph, the last one that we just made.
Yeah, let me zoom in on this. This one?
Yeah.
Okay.
So basically, I'm not familiar with PCAs too much, so I'm not sure how to interpret if we're not using PC2 as
Yeah.
like explaining a lot of the variability, I guess.
Yeah. Okay. Very good. Yeah. Let's talk about that, because yeah, we want to ignore PC2. So basically, what you interpret then is this left-right axis along the bottom. Okay. Don't worry about scatter along the Y. And when we write a results section for something like this, what we might write, the first thing we would say was PC1 explained 97% of the variation in the data and was the only axis that was needed that we retained for interpretation based on Pca significance. Okay. Vehicles with positive scores along PC1, so these here in this data cloud, were vehicles characterized by high engine displacement, low city fuel economy, and low highway fuel economy. Okay, so these, it's a gradient. Okay, so these vehicles on the gradient were characterized by those. And then vehicles that had negative values along PC1 were vehicles that were characterized by high city fuel economy, high highway fuel economy, and low engine displacement. Okay, so we're just thinking about these vehicles as they exist along this gradient that is PC1. And that's about it. I mean, there's no hypothesis testing here. It's totally heuristic. Sometimes, as I showed you in that early lecture on multivariate stats, we'll grab PC1 and that'll be our explanatory variable. Then we'll regress totally different things against that. And so, yeah, in the context of this one, this axis is the only one that you want. And so, you know, like these points are all vertical. They're all in the same point along that axis. But the fact that they separate vertically is irrelevant. We don't need to interpret that. Does that help at all, Natalie?
Yeah, thank you so much.
Yeah, so now PC1 is our axis. It's a linear combination of the original variables, so we can't pick out individual variables. Notice in my interpretation, I always hit all 3 of those in describing those vehicle characteristics. Cool. Okay, I'm going to end this recording.